In our lesson today, we'll be focusing on geometric series. All right, and your objective is that students will be able to derive the formula for a sum of a finite geometric series and use the formula to solve problems. We've actually looked at this formula in a previous lesson, so this should be coming as a slight review. In our activator, we took a look at this investment scenario, right? We took a look and we saw how there would be this common ratio we'd be multiplying by each time, and how that led to a slight increase in the amount of money that someone would earn in an account over time. All right, we're going to take a look at the math behind that structured savings plan. We're going to look at the sum of a finite series, and we'll look at some more applications of geometric sequences and series in this lesson. So let's take a look then at the math behind that structured savings plan. So in that activator, we looked at this particular problem where they put the money in the account and over time the interest was compounded monthly. This right-hand column, 100, 125 cents, 150 cents, etc., forms a sequence. We know that this is geometric, right? And the reason why we know that this is a geometric sequence is because there is a common ratio. All right, the common ratio is just that number that we're using to multiply each time. It's this 1.0025 or 0.25%. All right, what type of function would model the amount in the account after t months? Well, this would be represented by a function that is an exponential function, right? This is an exponential function. We could actually write an exponential function that would give us the explicit value for the amount of money after t months, for example. That exponential function that we would use could be the function based on time, where t represents the number of months, would be that initial value 100 times, and in this case it's the amount that we're multiplying, that common ratio raised to the t, where t, once again, represents the number of months that have passed, and the function f of t represents how much money is in the account. So let's say we took, and instead of just putting $100 in at the beginning and seeing how much it is at the end of a year, what if every single month we put in $100, right? Well, the first month we'd put in $100, and it would be able to accrue interest for 12 months. So that first month that you put something in, we would end up with that $103.04. That's the value that we would have for that $100. That's what that $100 becomes after a year. But in the second month, right, this is going to be $100 times, and if we think about our function that we created, it would be times that 1.0025 to the 11th. This one would be 100 times 1.0025 to the 10th, because over the course of the year, this one would be in the account for 11 months. This one would be in the account for 10, 9, 8, right? All the way down to the last one, which would only be in the account for 1 month to accrue interest. All right, so if we think about that, each of those dollar amounts, right? And this isn't the total in the account. This is how much money, that $100. So every month they put in 100. By the end of the year, it became 103. Month 2, they put in 100. By the end of the year, it becomes that value. You put in 100, it becomes that value. And every single month, that's going to change. Well, after an entire year, all right, the values would look like this. So that first one had 11 would have been in the account for 11 months, 10 months, 9 months, 8 months, etc. By the time we hit that last month, these would be the values in the account for each month after they're deposited. All right. So, and this is assuming we deposited the 100 during the first month. So that's why it wasn't 100 starting in the account that got deposited during that month. So it only accrues 11 months. Now, had you done it the other way, where you got the 103.04 and they were all shifted by 1, that's fine too if you thought about it that way. But we're looking at it, the last one gets put in right at the end of the year, so it has 0 months of interest, 1 month of interest, 2, etc. So by the end of the year, you have all these different dollar values. What's going to be in the account would be the sum of all of those dollar values, because that's how much money each of the $100 is worth by the end of the year. All right. So the total amount of money you would have at the end of 12 months, and that sum would be $1,216.64. Notice you've deposited $1,200, but you gain $16.64 in interest. All right. The calculations in number two, of each of those months, how are they related to the first scenario? Well, if we look back, all right, the first scenario, we had all of these dollar values, the 100, etc., all the way through. Um, and what was interesting about this is, these values, 100, 125, 150, 175, etc., all the way down to 10278, all of these numbers are all repeated, all right, in that last one. They're just in the reverse order. And the reason why they're in that reverse order is because we're just talking about what the value became over the course of a year. So this total that we came up with is really just the sum of that original table that we created. So we had this geometric series, and we could say, you know what? I wanted to find the sum for 12 months of that series to tell me how much money I would have after 12 months in the second scenario. Well, that's what we call the sum of a finite geometric series. And when we need to add many terms, it becomes way more helpful, instead of having to add them one by one by one by one by one, to have a formula to do so. Now, there's a story about a kid when he was 8 years old. It's a famous mathematician, Carl Friedrich Gauss. And the story goes like this, and I don't know how real this story is or not, but he was kind of getting on the teacher's nerves because he's a smart kid. He ends up being a famous mathematician, and the teacher, trying to keep him busy, is like, oh, what I want you to do is I want you to add all the numbers from 1 to 100. This is at 8 years old. For an 8-year-old to sit there and add all these numbers, it's going to take him quite a bit of time, right? The teacher thinks, oh, this task is going to keep you busy for quite some time, and he came up with the answer in seconds. He just said, oh, I got the answer. Well, how might he have done that? Right? Well, we've seen in previous lessons how that worked. He was able to find the sum of a series very quickly. And we asked, well, what kind of sequence is a set of integers from 1 to 100? This is an arithmetic sequence where we have a common difference between the terms 1 by 1 by 1 by 1 by 1. So if we ask what kind of sequence, this is arithmetic, right? Because we have a common difference between our terms. Now, so what kind of function would model that sequence, 1, 2, 3. If we remember, we could think of this such that the sequence a of n is equal to just 1, 2, 3, dot, 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 98, 99, 100, right? That's 100 at the end. All right, so we would say this would be linear, all right, and the explicit rule would be a of n is just equal to n. The first term is 1, the second term is 2, the third term is 3, etc., etc., etc. When we try to find the sum of the terms of a sequence, we call it a series. Well, Gauss computed the sum of the series very quickly, and how did he do it? Is he was matched up these terms. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. All the way up to 50 plus 51 is 101. There were 50 different times that we had pairs that added to 101, which would give us 5,050 as our total. That's how he was able to compute the sum, is he found a way to just get that sum. All right, he rewrote it essentially as this. He said, oh, well, 1 plus 100 times 100, all divided by 2. All right, and we could do that for any finite series. So in this one, 5 plus 8 plus, this should say 11, plus 14, plus 17, plus 20, plus 23. Notice we're adding 3 each time. All right, so our common difference is going to be 3. How might we use that same strategy to get that answer? Well, what we would do is we would take that first and last term and we would add them together. So it's going to be 5 plus 23 all times the number of terms. Well, how many terms are there? There are 7, all divided by 2. And when we do that, we would end up getting 98. All right. The interesting thing is the first one, all right, had an even number of terms. So everyone had a partner. In this series, we had an odd number of terms. So 14 was the middle term. It didn't really have a partner to add up to, but that's okay. All right, because the pattern still holds. It doesn't really matter. We still get the same values because we do 5 plus 23. Well, that gave me 28. 28 divided by 2 is 14. And you're like, well, why does it still work out? Well, because we're multiplying by the total number of terms. Because we multiply by 7, it still pans out and it works itself out in the math. So the general rule that we can use is just n times a of 1 plus a of n all divided by 2. That will get us the sum of a series, and it will work every single time. And sum doesn't have an e. So this next sequence, where we have 3, 6, 12, 24, 48, 96, 192, is a type of geometric sequence. And we know because there's a common ratio. And that common ratio is equal to 2. We're multiplying by 2 each time. A function that would model this would be an exponential function. All right, if we want to model geometric sequences, we use exponential functions, and the rule would be a of n is equal to 3, which is that first term in the sequence, times 2, which is our ratio, to the n minus 1. All right, and then if we wanted to find the sum, we could just add these values together. When we add those values together, we get 381. Well, with the arithmetic sequence, we were able to come up with a formula, essentially, to find the sum of a series. With a geometric series, we should be able to do the same. So there's an interesting thing that we can do if we want to develop a formula to sum the first n terms of a geometric series. All right, so let's start with that previous series that we were looking at. And we're going to look at that sum of those 7 terms that we looked at previously. We're just adding all those terms together. Now, we could rewrite that in terms of the series itself as 3 plus 3 times 2 plus 3 times 2 squared plus 3 times 2 to the third, etc., etc., etc. We can take that and we can multiply each term by 2. So we're going to say 2 times the sum is the same as 3 times 2 plus 3 times 2 squared plus 3 times 2 to the third, etc., etc. So we take each term in the sum of 7 and we multiply it by 2. And what ends up being really interesting here is that we end up having matching terms. That 3 times 2 matches the 3 times 2. 3 times 2 squared, 3 times 2 squared. 3 times 2 to the third matches 3 times 2 to the third. We have all of these matching terms. In my first part, sum of 7, I had a 3 standing by itself. In the second one, I have this 3 times 2 to the 7th standing by itself. So if I took that sum of the first 7 terms and I subtracted 2 times the sum of the 7 terms, right, I could factor out the sum of 7. This would become 1 minus 2 all times the sum of 7 terms of the first 7 terms. All right, and you might be like, why in the world are we doing this? Well, when we subtract all these pieces, these cancel, all these connecting pieces all cancel out, and I'm left with just this 3 and 3 times 2 to the 7th, right? But since I'm subtracting, it's going to be 3 minus 3 times 2 to the 7th, which we had here. I just kind of crossed it a little bit. So it's this 3 minus 3 times 2 to the 7th because we're subtracting. I can factor out a 3 and I get this 3 times 1 minus 2 to the 7th. And then if I want to solve for the sum of 7, I would just divide by this 1 minus 2 on both sides, and I end up with this little formula, which is pretty interesting. When I go ahead and I take this and I find the answer, when I do 3 times 1 minus 2 to the 7th all divided by 1 minus 2, we end up getting 381, which was the exact value that we got the previous time around. Well, we can take this, and instead of having numbers in it, we can take it and say, well, what if I take a series of n terms and I take a look at r times the series of n terms and I do the same thing. I'm going to go ahead and do, s of n minus r times s of n. And when I do that, right, I can factor out the s of n. I get 1 minus r times s of n is just going to equal a minus a r to the n. It's the exact same thing that we did over here in the first one in number 3. All right, once we have this, I can divide by 1 minus r. So I find out the sum of n terms is equal to, and I'm going to factor out an a from this first part. It's going to be a times 1 minus r to the n all divided by 1 minus r. And now I have a formula to find the sum of n terms of a geometric series. All right, and it's pretty kind of neat trick in just doing 1 minus r times the sum of the series to kind of get a formula for the sum of the series. But it works out, and we can use this formula moving forward to find the first n terms of any geometric series. So let's go back then to that first problem that we looked at when we had that $100 being deposited at the end of every month for 12 months. If I wanted to find the sum of the first 12 terms using the formula that we just found, it would just be 100 times 1 minus 1.0025 raised to the 12th, right, raised to the n, all over 1 minus 1.0025. And when I do that, I get 1,216.64. Does that match? It does. They're the same, right? That's the same number we got earlier in the lesson. So what does F equals S12 represent? It represents the total amount of money after 12 months of deposits, right? It's the same thing that we referenced earlier. And just to show you that it's the same, let's kind of look back, and we're just going back through those same slides. Oh, there it is. That same exact value, 1216.64. So we're able to do that. Now, we could take a look at this then as a series, and we could use this formula now to compute what we would call the future value at the end of a year, which we did in number 5, and we're going to develop a general formula for a future value without numbers, right? We want to write this out where all we have are variables instead of numbers, so it can be applied to any other situation similar to this. And so what this ends up becoming is just the rate r times 1 minus parentheses 1 plus I raised to the n all over 1 minus 1 plus I. Oh, that's hard to read. That minus didn't come out very good. 1 minus, that's better. 1 plus I, which this whole thing can eventually be simplified to just this. It's the rate times 1 plus I. This is just simplifying, getting rid of the 1 minus 1s, right? We distribute that negative 1 in each part, raised to the n, minus 1, all over I. All right, so what does n represent? Well, this is the number of payments, right? How many times are you paying that $100 into the account? What does the I represent? Well, it's the interest rate, right? That's where we got this 1.0025. It's the interest rate. What does R stand for? That capital R? It's the amount deposited each time. Now, that would have to be consistent for this formula to work, right? That amount deposited has to be the same every time. And if we go ahead and we use this formula to check this situation when we know those numbers, it would be 100 times 1.0025 to the 12th minus 1 all over 0.0025. So notice this is not the same as the one that we used earlier. But guess what? When we use this, it comes out the exact same. So we just generalized the formula and simplified to get the same value. So this is a way in which we can determine the sum of a finite series in which we have this interest rate. And this is just something that we can use for a future value for any annuity or any type of savings where you're depositing the same amount monthly and you're compounding monthly, etc. So in this lesson, we ultimately derived the formula for the sum of a finite geometric series. Afterwards, we learned that this formula, coupled with the modeling cycle, can be applied to solve problems about annuities, structured saving plans. We could even apply this to lease payments, loans, monthly home mortgage payments. If you look in the additional resources to the lesson, you'll be able to see some of those applications. You should be able to derive the formula for the sum of a finite geometric series and apply that sum formula to solve real world problems.